Okay, so we're going to next talk about the voltage stability tool for PV curves. In the next section, we'll talk about QV curves, but for this section, we're just going to talk about PV curves for now. And the idea of the voltage stability concepts is that voltage stability is the ability of the power system to maintain an acceptable voltage, both under normal operating conditions and after contingency conditions as well. Voltage stability tends to be a local phenomenon, but its consequences can have a widespread impact because of cascading effect. So a local voltage collapse can and does lead to a widespread collapse of the system if it's not handled in a timely manner. That's why we have voltage stability tools to help us analyze what might happen if we do have voltage that is going down or being depressed in an area due to some kind of an outage, for example. The ability of the power system to, or the characteristics of power system are the transmitted power P, the receiving end voltage V, and the reactive power injection Q. Those are what we're interested in looking at the relationships between for the voltage stability. The traditional forms for displaying these are PV and QV curves that we obtain through steady state calculation and analysis. And VQ sensitivities can also be used as indicators of voltage stability, primarily in not only the magnitude, but also the sign of those sensitivities and making sure that the sign of the sensitivities are correct for the analysis. So we're going to focus on a PV study or power voltage study for the current section S6 that we're looking at now. This process involves using a series of power flow solutions for increasing transfers of megawatts and monitoring what happens to the system voltages as a result. The relationship of voltage to megawatt transfer is nonlinear, which requires a full power flow solution. What this means is that we're going to be doing an iterative process where we're going to be repeatedly solving power flows for transfers or incremental transfers between a source and a sink. And it's going to be a full AC power flow for each iteration. So because of that, it can take some time to run a PV study depending on what you're doing and how big your case is and how many different branches and how many different buses you're monitoring and how many contingencies you're including. All those things are going to factor in for your PV study, and so be aware that a PV run might take some time because of the fact that it's doing repeated full AC load flows for each step. You'll see where that would come into play when we start doing an example. So traditionally, a megawatt transfer is designed to model increasing load in part of the system. Specific buses have to be selected for monitoring, and PV curves are plotted for each bus. So oftentimes when you do a PV study, you've already got an idea of what buses might be an issue or that you're interested in looking at for a particular transfer. You would select those buses to monitor during the PV study, and then you would run a PV analysis and be able to plot the curves for those monitored buses when you're done. This is what a typical PV curve plot would look like. Note that it's a parabolic shape, so it's a very nonlinear curve. Nonlinearity is the reason that faster linear sensitivity methods cannot be used with the PV curve analysis. So we can't use sensitivity analysis with linearization of the sensitivities or the derivatives of the curve. We have to use the full AC load flow to solve for multiple points along the curve to determine the shape of the curve. So we always have voltage on the y-axis and the power transfer on the x-axis, and our critical voltage occurs at the nose point of the curve where we have the maximum transfer. If we tried to transfer power from the source to the sink beyond this maximum transfer point, we would end up with a load flow failure. So basically you're at the point of voltage collapse. Where you want to operate is usually somewhere up in here. When you're getting out in here towards what we call the knee of the curve, your voltages are going to be dropping faster, your sensitivities are going to be increasing. So as you have a smaller increase in power transfer, you're getting larger drops in voltage. A lot of times when someone is analyzing and looking for this critical voltage, what they're really looking for is what's my maximum transfer, and then they will design whatever they're doing so that the maximum transfer they set is actually something back here. They want to know what this is, but they really then back it off, and they'll say, well, my maximum is really back here because I don't want that rapid decline of voltage if I get too close to this point. So the knee of the curve, the voltage drops rapidly with an increase in megawatt transfer. Power flow solution fails to converge beyond this limit, which is indicative of instability. We've talked about maximum power transfer many times in electrical engineering courses. This is the same thing we're talking about here. Operation at or near the stability limit risks a large-scale blackout. A satisfactory operating condition is ensured by allowing sufficient power margin. So we have a PV curve example that we do in this training section. It's based off of a fairly old Midwest case called Midwest.raw. It's about 10,000 buses. And we already have defined some injection groups, some options, and a contingency that we're going to use to do a PV example. So we will be opening that up momentarily. We're going to study a power transfer from generators in MAP, which was an area in Minnesota, to an increasing Wisconsin load. The first step of that is defining an injection group containing the MAP generators to serve as the source. The injection groups in simulator PVQV define which region or regions will import the transfer and which region or regions will supply it. These are discussed in section I5, data aggregation. That section talks about how you define injection groups, and which is what we're going to need here for the PV analysis. These groups act in unison to implement a power transfer. One side is the source and the other side is the sink. So we're going to go ahead and open a simulator and open up this case, and we'll work from that case to do an example. So I'm going to go over to simulator and I'm going to open a case, and the case I'm going to open is in training cases, and it's a raw file, so I want to change my file type to raw. It's right here in the main folder, midwest.raw. So we'll go ahead and open that. So as I mentioned, this is about a 10,000 bus case. If I just go quickly look at the case information, and I can look at case description or case summary. My case summary tells me how many buses, generators, loads, etc. are in this case, so I can see roughly the size of the case I have here and where my slack bus is located, which is at Browns Ferry and TVA. So I can get my information from there if I wish about this case. So what we're going to do is we're going to be doing the PV analysis, and the PV analysis is an add-on tool for simulator, so you're going to find it under the add-ons tab on the ribbon at the top. And there's a PV curve tool button here, so if I click PV, it's going to open up to the PV curve dialog, and it's going to open up to the setup page. So here we define first what we want to include for the source and the sink for this analysis. The only source and sink you can choose for a PV analysis is an injection group. So you do have to define your injection groups before you can run a PV analysis. So I can go to View, Define Groups. And if you had gone through section I5, you would have gone through how you create an injection group. Very quickly, how you would create an injection group is you would right-click and choose Insert. And this opens up a default injection group dialog. And then you need to insert your injection points. And your injection points can be generators, they can be loads, they can be a combination of the two. You can include shunts in your injection group. You can include another group in your injection group. So if you've already defined one group and you want to add it to another, you can do that. You can add just individual buses to the group. But of course, if a bus doesn't have a source or a sink on it, it doesn't really do anything for this analysis for the PV tool because there's no injection there. But what we would do here is we would set up injection groups for MAP, and we would set up a generator injection group. So we would use area zone filters perhaps, and we would go define what those area zone filters are. Area zone filters, which I can edit down here. So I could go through here and I could right click in the shown column and set toggle all to no. And then scroll through and find map, which is down here, area 88. Toggle that back to yes. And then just close the area zone owner filter. And now all the generators I see currently in this table are only the map generators. I've told it to filter out everything except for that. So now I can select all. And before I add them, I have to decide how I want them to participate in the transfer. I can use their present participation factors, which is probably some number based on the size of the generator in terms of megawatt limit. But I can also do things like base it on positive reserve, which just means it will calculate a participation factor for each generator that is the difference between its maximum output and its current output. And what that would do is, as it ramps up the transfer of all the generators, it would ramp them all up so that they all hit their limit at the same time. There's other ways you can do it too. You can base it on megawatt capability, which is typically the default for participation factor, is it just bases it on size. If one of the units that you add is already at a limit, it won't try to go above its limit as long as it's set to enforce megawatt limits, so you don't have to worry about that. Once a generator hits its limit, it will just take the generation from the remaining units in the case. And we would do something similar for loads for Wisconsin. If we were going to do loads, we would again perhaps change our area zone owner filters to include only the areas in Wisconsin, and there are a few. There might be Wisconsin Power and Light, Wisconsin Electric, Wisconsin Public Power, Madison Gas and Electric, Upper Peninsula Power, which is part of Michigan as well, etc. So we can include these and close this. And now all the loads we're looking at here, when we click Use Area Zone Filters, these would all be all loads in Wisconsin and Upper Michigan. And again, I could select all, and I could add them based on size. So it would create a participation factor for each load just based on the size of the load. So larger loads would increase faster than smaller loads. And we could add that in and create a sync group. What I'm going to do though is we've already created these. So I'm going to right click and I'm going to go down to load, and I'm going to load an auxiliary file. And the auxiliary file that I want to load is called midwestinjectiongroups.aux. It's probably in the S06 folder. Here we have midwestinjectiongroups.aux, so I'm going to open that. It will ask me if I want to define the groups because it recognizes they don't currently exist, and I say yes, I want to do that. And what this is, Wisconsin Upper Michigan System. It's what WUMS stands for, and I want to create that as well. And so it creates two injection groups for me and adds them into the injection group table. I had already created them previously and saved them to that aux file. And I can see that I have a map injection group of 374 generators with a total megawatt injection of 31,000 megawatts. And I have a load injection group of 574 loads in Wisconsin and Upper Michigan with a total load demand of a little over 10,000 megawatts. So I have these two groups defined, and what this is going to allow me to do when I do my PV analysis is define map as my source and WUMS as my sink. And so I will be transferring power from increasing generation in Minnesota to increasing load in Wisconsin and Upper Michigan. So that's what my PV analysis is going to do. So I have those injection groups defined. So that's my first step for the PV analysis, and that allows me now to go select my source and my sink because my two groups are now present. So I'm going to set my source as the map generation and my sink as the WUMS load. So now I have my transfer defined. So the next thing I'm going to do is look at what the options are for the PV analysis itself. So for example, how many critical scenarios do I want to find? And what this does is it tells simulator to run the PV analysis until this number of critical nose points on a curve are found. Because what's going to happen is it's going to solve the power flow, it's going to increase the transfer by a step size, which is defined down here, and it's going to solve the power flow. And if everything solves fine, it's going to increase it again by the same step size and solve it again, and increase it again and solve it again. It will increase by the initial step size until it gets to a point where it increases by another increment of 100, and then the load flow fails. And what it will do is it will restore back to the previous solution. It will reduce the step size by some factor of reduction that we define here. So it's going to reduce it by a factor of 2, so it's going to cut it in half. So it's going to cut it down to 50, and now it's going to start ramping in the transfer by 50 megawatt increments until it fails again. Cut it to 25, increase by 25, cut it to 12.5, and eventually at 12.5 it will fail, and it'll try and cut that 12.5 down and to 6.25, and it'll realize that 6.25 is less than my minimum step size I've established, which is 10. So it'll set the ramp amount to the minimum of 10 and then keep ramping out by 10 megawatt increments until the load flow again fails, and then it'll back up one step to the last solution it obtained and stop. So that's how it tries to hone in or get close to where that knee or critical point is on a curve. The number of critical scenarios here means that when it hits a critical scenario, it will stop. Now, that critical scenario might occur in base case conditions, or it might occur under contingency. And we can choose to include contingencies. We can manage a contingency list, and we can go and create contingencies. And again, you could insert by right-clicking here, create or load an auxiliary file, which already has an ARPAN contingency defined, so I can open that. And it tells me it's not defined and asks if I would like to create it, and I say yes. So it has created a contingency for me. I've just created one contingency, that is the ARPAN to Eau Claire line. And you'll see if I look over here in the definition, it tells me that this contingency makes up a double outage. It's the loss of the ARPAN to Eau Claire 345 kV line, which historically has been a critical 345 kV path with stability issues between Minnesota and Wisconsin. And it also opens an underlying 115 kV line that is somewhat parallel to this line between, I think it's Wien to Tri Corners. So this is a double outage of these two lines that we're going to be analyzing, and because traditionally we know that this has some voltage implications in Wisconsin when this particular contingency occurs. So we have a contingency defined, so we can include the contingency. If you have contingencies defined and you don't want them included in the PV, you can skip the contingencies by checking this box. We do want to include it for our example, so we're going to leave it here. You can also choose to run the base case to completion. What this means is that if you have multiple contingencies defined, but you've got it set to stop after one or two critical scenarios, it's going to stop solving after it finds two contingencies or three contingencies, whatever you have it set to here. It will stop whenever it hits that number of contingencies that reach a critical point. But you can also tell it to go ahead and just finish running the base case all the way out to its critical point as well, independent of what you have set here for critical scenarios. So that's an option that you have for just letting the base case complete. And if you want the base case solution options to be different than what they typically are in the simulator options, you can come in here and modify those options. So you can modify the base case solution options here. Under the contingencies, we didn't talk about it, but in the contingency list, there are options under contingency that you can choose different solution options during contingency than during the base case. So you have the ability to do that as well. By default, they use the same options. But now we have our source and our sink defined. We have our contingency list defined. We have the number of critical scenarios defined, and here I'm just going to leave it at 1 because we only have one contingency defined anyway. And we have our transfer specifications set as to how it's going to ramp up the transfer, change the step size, and when it's going to stop. You can also have it stop when the transfer exceeds a certain amount. So if your transfer gets up over 2 gigawatts and you say, well, I would never transfer 2 gigawatts from this source to this sink. So if it gets that far and it hasn't collapsed, great, just stop trying to calculate it. So you have the ability to just have it stop after a certain transfer amount. So once we have our options defined, we can go to our quantities to track. And here in our quantities to track is where we now choose what buses we want to track voltage at for the purpose of plotting the PV curves later on. Note that you can also plot a lot of other things or track a lot of other things if you want to as kind of a subsidiary to the voltage. The primary thing we're looking at here is what's the voltage doing at certain buses, but you can track a lot of other things too. You could track changes in angle, you could track changes in load, you could track DVDQ sensitivities as the transfer ramps out. So you can have it tracking and storing values at all these different buses of various kinds if you have a need to do so, and you can then look at those values or plot them versus the transfer just the same as you would plot the voltage versus the transfer, which is the PV curve. So you have a lot of other things you can do, but the primary thing that we're interested in the PV curve tool is this column right here, which is we want to track voltage at certain buses for the transfer. Note that you can also track some generator fields. You can track some line values like branch flow or losses. So there's a lot of things you can track, but the most important one is this voltage for the buses. Now these have already been defined for us in midwestpvoptions.aux. So if I go down here to load auxiliary, I should be able to open the midwestpvoptions.aux file. And it will come up with, and it'll say that branch track limits is not defined. Do I want to create that? I'll say yes. And so I should have, after loading these options, 2 buses that have now been flagged for plotting PV curves. If you just click on the heading for a column, it will sort the column. If you just click on it again, it'll sort it in the opposite direction. So if you just click on that a couple of times, and it will sort. And you'll see that we do in fact have 2 buses now that have been pulled to the top that have been set to voltage being monitored. So these are the 2 buses that we're going to monitor during the PV run, which means that at every solution of the PV analysis, it's going to store what the voltage was at those 2 buses, so that when it's done, you can plot a curve of those voltages. So once we have our quantities to track set, we're pretty much ready to go. There's some limit violation settings that you can look at here before we do that. You can have it additionally to storing the quantities that you're tracking. You can also have it identify buses that have low voltage violations based on the limit monitoring settings, and also high voltage violations if you want. You can have it stop when a voltage becomes inadequate, and you can define what to store as inadequate voltages. Do you want the low voltage, the high voltage, or both to be considered inadequate? There's also a voltage level to consider inadequate. So if I say stop when voltage becomes inadequate, you can specify what an inadequate voltage is. So if it falls below 0.9 in this case, it would stop whether it's reached the critical point or not. So I'm not really interested in this, but it's something that you can use for additional analysis. You can also have it stop if a DVDQ sensitivity becomes negative. What that means is that you've gone to the low voltage side of the curve, but it's still solving the power flow, which can happen. So sometimes you may want to choose to stop when the DVDQ sensitivities become negative, because you don't necessarily want to keep trying to solve if you've gone to the low voltage solution, because the voltages are still going to be going down, but they're going in the wrong direction in terms of trying to find the nose point or the knee of the curve. So that is an option that you have as well for stopping the analysis if you hit that situation. And so if I go to PV output, now I can save the results to a file if I choose, so that when it runs this, it will save everything out to a text file that you can open up in Excel or WordPad or whatever you might choose, and you can actually look at the raw data if you wish. I don't know that we need to do that in this case, so I'm going to uncheck that. But it just gives you an option, and the transpose of results just makes it easier for you to see in an Excel sheet, I believe, if you want to look at it that way. You can also archive states, which means it will save a binary file periodically while it's solving the PV analysis. You can have it do it only for the base case for each critical contingency, or you can have it do it for all states, which means it would save every iteration of the solution process. Every time it increments the transfer and resolves the power flow, it would save a case with that system state. So you can imagine it might save a whole lot of cases. But you don't have to do that, but if you choose to, you can set it up to archive states and tell it where to put them. I'm not going to save any for now. I'm just going to solve it and look at it right here in Simulator. So I'm going to go to the PV results page, and in the PV results, this is where I can go ahead and run the PV analysis. So I've got it all set up. I'm going to go ahead and click run, and it's going to start going through and ramping up the transfer amount. So you'll see it's increasing by our initial step size of 400 megawatts. So what it's doing right now is it's increasing the transfer by 100 megawatts each step, and it's solving the base case and it's solving the contingency scenario. So it will go through, ramp up the transfer, and solve the base case and each contingency case. And so we'll see it keep going up here by 100 megawatt increments until it gets to a point where when it adds 100 and tries to solve, it failed at trying to do 2000, so it went back to 1950. Then it failed again, and we ended up getting up to 1960. It failed to solve at 1960, so it has stopped because we told it to stop after finding one critical scenario. So it has stopped because the contingency has caused it to reach a nose point on the curve at a shift of 1,950 megawatts. And so it tells me what that shift was. And I can scroll over a little bit and see at that point it had a mismatch of 0.1568 megawatts that it was unable to resolve, and 0.3633 megavars that it was unable to resolve, which is greater than our tolerance of 0.1. So that's why it stopped and said, I can't solve this because I cannot get these two values below the tolerance. And it tells me what bus that occurred at. So this bus right here, 39699, Whitcomb, was the one that was unable to resolve its mismatch and allow the load flow to solve. So now that I've got my curve finished, I can go and plot. So I can set my horizontal axis to be the nominal shift. That's this number up here, so my present nominal shift. I can set my vertical axis to be the per unit voltage, and I was tracking two values of voltage, so I'm going to double click plot to yes for both of those buses at Spring and Arpin. I also, over here, I'm going to choose to plot them for both the base case and for the contingency scenario. And once I have set my axes and I have set which values I'm going to plot and for which scenarios I'm going to plot them, I can click plot down here in the corner, and it's going to create a plot for me of the PV curves. And note, it really only plots the upper half because we're marching along this part of the curve. We didn't go down to the low voltage part of the curve and try and calculate a whole bunch of data points to plot the lower half. All we were doing is marching along these curves towards the nose point. And you can see we have this blue line is the base case for Spring. We have the light blue line up here is the base case for the Arpin 138 kV bus. Red is base case for Arpin 138, and green is the contingency scenario for Spring 138. And so we can see where we were collapsing here in terms of voltage was more so at the spring bus under the contingency. When you see your plots up here for the ARPAN bus look like this, what that means is there was some form of voltage regulation going on. So you can see where the steps were occurring, where we had some voltage controller that kept switching in either taps on a transformer or adding VARs at a switch shunt to try and hold the voltage up. But eventually it runs out of capability to do that. And as I mentioned before, as you get close to the knee of the PV curve, the sensitivities get larger and the voltage is dropping more rapidly. So that's why you see the curve here start dropping off faster at ARPAN, because the voltage control is running out. Also notice that it's actually a little more stable at ARPAN under contingency than it is spring. Spring is better in the base case, and it's worse under contingency. By having that contingency, we've actually made the voltage stability perhaps a little bit better at one bus, but we've made it worse at the other. And this is the one we really care about because it's dropping off rapidly. It's dropping well below what I would consider acceptable levels. It's already below 0.86 here at this point at 1950. That's an issue, and this is what we're looking for, is that at this point right here is essentially the nose point or the critical point of the PV curve. So for this transfer of 1,950 megawatts, we can plot these curves and determine approximately where we have an issue with the nose point of the curve and what levels of voltage we're getting down to at that point. Again, you can track lots of things, and if you track additional things, you can plot and add them in here, and you can create plots for additional things like flows on lines and things like that during the transfer if you want. This is what we call a more advanced plot designer, and this actually lets you get into it a little bit more detail to plot things. So for example, here I can identify objects by number. I can choose what type of device I want to plot for. So I'm going to plot for a bus. I want to plot the per unit voltage, and then I can choose where I want to plot that value from. And of course over here I can see that I have my transfer amount here, and I was tracking the per unit voltage at these two buses. So I can choose to plot these voltages here. If I go ahead and generate the selected plot, it's still going to generate basically the same thing that it generated previously. It just looks a little different. And you can actually choose what to see on here by just checking or unchecking. So if you have multiple plots on the same plot table and you want to hide some of them, you can do that here. So this is just a little bit different legacy, or this is a more advanced plot designer. I tend to find myself not using this as much as I just use the basic plots, because that's what I'm used to. This was added in later on for more flexibility and for being able to do more things with it, but you get essentially the same thing out of it. So you can use this, and again, you get to this if you go down to plots and then go into plot designer, and you have a lot more things you can play around with here for plotting and choosing what you want to plot and what you don't want to plot. And you can add new plots here if you want to add things to it that you want to plot that are other than what it by default has stored based on what we tracked. There are some advanced options related to the PV and some ramping things that you can do, so you can play with how things are ramped for the injection groups if you want to build ramping into it. You, for example, instead of just ramping up all the generation by source of the source and sink proportionally, you can actually choose to do it by merit order. By the participation factor in the injection group, you would basically sequentially number them, and I believe it will do it based on the lowest participation factor number first. So you would have to go modify the participation factors to instead be a sequential order that you want the generators to, or the loads to increase or decrease. And you can do it by merit order. Instead, you could do it by economic merit order if you have economics data with the generators and so on. So there's different things you can do here with how the devices inside the injection group participate. Every generator has a participation factor generically.
Right.
It's usually based on the megawatt capability of the unit. In the injection groups, however, you specify a completely different participation factor if you want. You can use the original one, but most of the time people use something else and they set it to a participation factor based on how they want it to be used. Some people set it based on the reserve left on the unit so that they all hit the limit at the same time. Some people will sequentially number them so they can do a merit order dispatch for something like the PV analysis. Instead of having them all dispatch together, they dispatch one at a time. So you have flexibility, and how you define those participation factors in the group will dictate how it responds when you use it as a group. And then there's a few other advanced options related to how reactive power should change during ramping. Typically, as megawatt changes, you can change the megavar at a power factor of X. In this case, if it's 1, it means megavars aren't changing. You can also say how do load components vary. All changes apply to constant power, or do you want to vary them proportion to existing zip model ratios, or do you want to vary them using values you specify down here? So you can get really complicated with how you allow your loads to respond if you include loads in a group. The simplest one is just to let only the constant power values vary, and if there are any constant current or constant impedance values included, they just don't change. It's only the constant power values that change. And then if you want to apply a reverse transfer, you can have it go in the opposite direction. I mean, it's basically you're going to go from where you started, and then it's going to switch the source and sink and go the opposite direction. And so you can do a maximum reverse transfer limit here when you do that.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.